computing, 3D printed rockets, AI platforms for small molecule and protein therapeutic discovery, programmable mRNA platforms, so that's the world we live in. And our Robochat series is meant to bring leading experts in the fields of deep tech, robotics, AI, automation, next-gen compute to discuss their thinking, their ideas, challenges, predictions, and anything else where the conversation takes us. All right, before we get to our amazing and distinguished guest, a few quick housekeeping items that I'd like to cover. So this event is being recorded and will be shared following today's live session. You can find all of our Robochat recordings on the Playground YouTube channel. Please do go and view some of the previous discussions we had about the companies that I just mentioned earlier. If you have any questions for Professor Anima, today's guest, please submit your questions via the Zoom Q&A feature. You will have the option to upvote questions that are submitted. I will also read questions that were pre-submitted during the conversation. If you have any technical issues or would like to contact the event organizers, please use the chat feature. All right, on to our guest. Professor Anima Anandkumar is a Bren Professor at Caltech and Director of Machine Learning at NVIDIA. I wore my special shirt for this event because I used to work at NVIDIA prior to Anima joining. Anima, you are also the youngest named professor at Caltech, which is really the highest honor bestowed upon a faculty member. That is truly amazing. Previously, you were a principal scientist at Amazon Web Services. You received numerous honors such as Alfred P. Sloan Fellowship, NSF Career Award, Young Investigator Award from DoD, faculty fellowships from Microsoft, Google, Facebook, and Adobe. And you are part of the World Economics Forum Expert Network. Wow, that's a lot. Can you remember all of that?
Well, I like to think about the people I work with and the amazing science I get to do. That is much more something I cherish.
And you had this fantastic blend of theory, research, and practical applications of AI. I really admire that, and it's not very common to find people like you. So today's discussion, what I would like to do is kind of set a baseline understanding of AI, then talk about the current state of AI, and then talk about the future, the next frontier. And then, sprinkle in audience questions, pre-submitted questions within the context of our discussion. Sounds good?
Sounds like a great plan.
All right. But before all of that, a little bit about you. Your life story is just fascinating. Actually, you embody what I often see in individuals who end up having a remarkable impact in the fields of science, tech, or business. And that is a childhood interest that requires focus, passion, and discipline. In your case, that was Bharatanatyam. I hope I said that right. It's a major form of Indian classical dance. You once said, if you didn't end up in tech, you would have been a dancer. Any regrets there?
Not really, because I get to dance in my mind and in my soul every day with science, right? And it's really that aspect of exploration of the unknown. And with dance, it was exploring the movements, what my body is capable of, and the rhythm, like it's really connecting with the world and with the nature out there. That's what I felt when I started dancing as a kid, because I felt like, that was the first time. It really made sense, right? The movements, how the body would move with music and would just kind of take a life of its own. And it's the same I feel when I'm doing math, right? It kind of like go so much into that focus that, it takes over everything. And so in that sense, I see the beauty in dance, I see the beauty in math, and they're very connected.
Yeah, I really like that, the connection that you described, how you stretched your body and physical aspects of what you can do as a dancer, and now what you do, you're stretching what your mind can do and what you can discover. Now that is amazing. And like I said, I really find that in a lot of successful entrepreneurs, scientists, researchers, you can trace that back to some childhood passion that actually instilled the discipline and focus. That is really remarkable. All right, so to dive into our topic of AI, let me share something that I kind of put together in thinking about our thesis here at Playground about AI and the AI lifecycle. Hope everybody can see that. Basically, I tried to map the evolution of AI, from fiction, early legends, and fantasy about what robots will do with us, and how we'll be ruled, and then the theory behind it, the math and the science, and then how it finally became practical from theoretical, a lot of people just thinking about it and assuming this can be done, and then all of a sudden, with ImageNet, AlexNet in 2012, we realized actually we have the compute power now to do this, and the trigger that was the discovery that you can use the massive parallelism of GPUs to actually run these algorithms and detect cats and dogs, hot dog, not hot dog, and things like that. Now that when we realized we could do that, then we realized, wow, we need to productize this, harden it, create a rugged MLOps stack so we can run enterprise class applications. And that's what we have now for predictions, for NLP, and so forth. But we still haven't achieved, in my mind, the mission critical readiness of AI. We don't really trust it yet. And I think that's the next step in this evolution. And I try to kind of map, we are here in this little gray area right in the middle in this 100-year journey, until we maybe someday get to some form of general AI, that applies some kind of reasoning. And the trigger for that is, I'm using robustness as the word, the way Gary Marcus defines robustness, and that means some kind of cognitive capability and applying learnings to new domains and things like that. All right, so that's just kind of to set the stage. And next, I would like to ask you to talk about, in your TED Talk from way back 2018, you talk about the Trinity of AI. Sounds almost religious, but can you just set your baseline? Any step your thinking has evolved since then, or if you have new ideas there, that would be really great to hear as we move through this progression.
Yeah, indeed. The reason I mentioned it as a trinity is these three important components, right, that led to this AI revolution. I mean, you put the GPU compute as the one that made that leap from theory to practice. And indeed, that's an important one. And that's the one so many people, especially the general public, would miss, right? Because that is hidden, right? But that large scale computing was essential, but also the parallelism and the availability of linear algebraic primitives, right? So without those matrix operations readily available in CUDA, you couldn't just easily go build such a large neural network. And so the other two facets, the neural networks and all the flexible modeling that goes with it, right? That's one. But the third one that's very important is data, right? So without the creation of ImageNet, we wouldn't have this deep learning revolution, right? Or such similar open data set that is labeled. And for the first time, it was millions of images available to researchers. And so that really had, again, a quantum leap in terms of the data that was available. And without that availability, we wouldn't have seen the power of neural networks. And so that's why I call it the Trinity. And that was a great beginning. But now the aspects, right, of where we go next, as you said, productionizing it is very important. Now we're thinking of models that are enormous, right? Billions of parameters, if you think of the latest language models, and training that on thousands of GPUs. So how do you easily enable researchers to write code? I mean, they're not system designers or engineers, right? So how do we make it easy to run that large scale benchmarks and further improve upon that? But the other important aspect is data for such large scale models, right? Because the routine thinking in machine learning is, you keep training. If something goes wrong, you retrain again, right? Or you go tune others, or you go filter out data if some data was problematic. But in fact, if you see in the GPT-3 paper, they even have a sentence there, we realized there was some leakage from training to validation set or test set, but we can't retrain because it's way too expensive. So requires a completely new thinking when the amount of resources becomes that enormous, right? So it requires a lot of planning, but also these aspects of then what is the right kind of data to choose for such a model. I mean, we've seen a lot of problematic issues with the data bias, and we can't keep training these models every day. So we have to be mindful of the resources we use. So that to me is one progression, right? So further just increasing this model complexity. I think there's a statistic like it has increased to 30,000 times in the last 5 years, right? It's doubling every 2 months. So this is like the new Moore's law. But the thing is, like any law, this will also plateau, right? We can't just afford to keep increasing these models and keep growing them without limits. And so the next aspect becomes more intelligent algorithms. So how do we create better inductive bias, create better neural network architectures that are not so data hungry, right? Or can work in a self-supervised manner without labels or have just weak supervision. And so there's a lot more play in the algorithmic development, because just brute force basic algorithms will not cut it because we can't afford to just keep increasing the model size. And then the other aspect is so many applications cannot afford to have large models, right? So especially on the edge. So the edge revolution is just beginning. And if we want to think of a smart everything revolution, we have trillions of connected devices, each having just limited battery, limited memory capabilities. How do all these models talk? What about privacy, security, all these issues involved, right? Ultimately, you want them to make decisions. You want them to exchange relevant information and have their own AI. And that, I think, is a whole different realm of challenges involved.
All right. So you touched on a lot of topics that I'd like to kind of dive into. So the holy trinity is data, algorithms, and compute. Data is enabled by all these sensors and data collection that we have in massive cloud capacity. Algorithms were kind of around even before it became practical, but now they are supercharged and evolving. And then compute as well is evolving. So how would you describe the status quo? You kind of touched on it there, but what are some of the main problems that you can kind of identify? And then we can dive in, what are the possible solutions in the future? But first, like main issues that are just not sustainable or scalable, beyond where we are today.
Yeah, so indeed, starting from the compute angle, right, as I said, the MLOps and making all that easy to program and run it on large GPU cluster is a great beginning. But the next step is, how do we make the hardware more efficient and better, right? So indeed, we are having more powerful GPUs, but also the question of like this convergence of high performance computing and AI coming together. The world's fastest supercomputer that was recently announced, ALPS, will be 20 exaflops of AI compute, right? Whereas traditionally HPC was 64 floating points, and then that required very high precision in the compute, but we are no longer talking about that. So this convergence of AI and HPC is really important for scientific computations. So we are no longer relying on brute force computations that need to be performed at very high precision. Instead, AI can leapfrog and not only give speed up on those methods, but also be able to do that in lower precision. So that's one way to make very good use of existing hardware, right? Even as we are seeing its limits. The other aspect is the convergence of GPU and CPU being much more closely integrated. There's the NVIDIA Grace that has been announced along with GPU. So if we can make all that back and forth be very efficient, we can get a lot more out of the current computing capabilities. And of course, then there is the longer term in the hardware, right? Whether it is in terms of, what is the level of precision do we need? I mean, right now we are saying FP16. I mean, can we go to FP8? Can we ultimately go to binary? Can we in fact go to other systems like logarithmic number system? This is something we found to be very effective. And in fact, there is evidence the brain also stores it in a logarithmic number system. So all these aspects, right, again, that would be a co-design of algorithms, co-design of like how we want to represent these systems and the hardware efficiency that goes with it.
So the tight integration of algorithms and hardware, and tighter integration of hardware itself too. You mentioned CPU and GPU. What about new computer architectures? Any thoughts there beyond just von Neumann, where you separate all these major components like memory and processing? Do you see any advancements in core hardware as well? Whether NVIDIA or outside, it doesn't matter.
Yeah, I think certainly this is now, an area seeing a lot of development, right? Like, the whole idea is, can we move data quickly and can we have compute closer to data, right? This is, always been an idea, but now we're seeing more developments there. And ultimately, like, we said, if, we are thinking of lots of edge devices, right, with limited bandwidth, that's also a very different paradigm, right? Because now, you have to ask what we can do locally. And if there are privacy constraints, there's further like federated learning and other issues to be tackled. So it won't be one size fits all, right? There'll be lots of heterogeneity, and we would have to have algorithms that can also adapt to these different hardware conditions. So that's, I think, an aspect to think about. I mean, especially if we are thinking of launching it in Mars rover or even on Earth in, say, fire or other hazardous conditions, we cannot rely on cloud connectivity, right? When we cannot rely on, full battery. I think so. Like an AI that is intelligent to understanding what the current hardware capabilities are and plan based on that would be very essential.
All right, so let's talk about the massive data sets. You've touched on this. That's not sustainable and scalable either. So what areas of research are you aware of there that will actually reduce the need for massive amounts of data, or maybe, new greenfield approaches?
Indeed. And I mean, it's been said the data is the new oil, right? But at the same time, we are saying we should reduce oil dependence. So I see that apt because, we cannot just rely on the massive amounts of data, especially because at that scale, like I said, when training, say, GPT-3 model, we no longer have a handle on what we are feeding it in, right? Is this the right kind of knowledge and information we should feed this? Is all the hate speech, toxicity, bias? It's just not possible to have humans involved at that scale. So now we are reaching to that level. And so one aspect is, of course, better algorithm design, right? That could, like, in a way, ultimately self-diagnose and understand, right? Like, as, you put that as the last block of reasoning, but some aspects of it, we're seeing that now also being implicitly done in the attention layers of the transformer. But if there are ways to explicitly, let's say, check against a knowledge base, right? I mean, we have lots of knowledge bases. So check for consistency and kind of, enable this kind of internal consistency within these models. Then I think, like, instead of just blindly increasing the amount of data, we could do more with even the current data. And the other important aspect is building realistic simulations, physically valid simulations, if we are thinking about robotics and domains where it's just impossible to run 1 billion runs of a robot arm, right? So we cannot replicate AlphaGo on these systems in a naive way. And so in NVIDIA, what we're doing is the Isaac platform, where we have GPU accelerated simulations, so we can run thousands of them very easily and then seamlessly transfer that to the real robot. And so that requires like hierarchical learning algorithms, right? We cannot overfit everything to the simulation. We can't possibly get friction and other parameters correct. And of course, if we are using perception, it would be very different from going from simulation to real. So these kind of domain adaptation algorithms that can generalize, right? So and that kind of goes to the robustness you talked about. So in a way, it should not just work in that simulation environment, it should be able to go beyond. And so that again opens up a lot of opportunities for algorithmic design.
Yeah, simulation is an interesting one, especially in the context of robotics, because you're simulating the physical world without any of the physical world stimulants or conditions, the environmental conditions. You mentioned you cannot easily or accurately simulate friction, but there's a lot more like, humidity and heat and vibration and all these things. So in the self-driving industry, how do you, or autonomous mobility industry, how do you validate safety? Well, it's some form of combination of simulation and real world driving. And nobody, I think, has a good answer yet. What is the right balance to prove that safety because of the environmental factors? I don't know what the answer there is.
Yeah, I mean, it's indeed a complex question, but this is where, having an interdisciplinary mindset can help us bring these different areas together, right? Because, this is very well developed in control systems, right? Like having safety barriers, guaranteeing stability. But the problem is they've been done only in low dimensional systems, right? So they're not built for like perception, or they're not built for black box systems like what neural networks are doing. And so what we need right now are the right abstractions and these interface, right, between what the AI system will be doing and how it interacts with these traditional tools. And so one of the things we've been working at Caltech is to enable drones to fly safely, even at very high speed winds, ultimately hurricane level winds. Right. So, and that kind of adaptivity requires a mix of deep learning along with traditional methods, right? So by traditional control methods, with deep learning, we can learn the general representation of how different wind conditions look like. But then online, as the wind is changing, you do want online adaptivity, right? And there are real-time fast control algorithms that can, easily learn linear parameters over the learned representation and do this adaptivity. So, and similarly, in another project where I mentioned the use of simulations, what we did was to have a hierarchical learning, meaning in simulation, we are not learning from scratch on, say, this four-legged robot, right? It knows how to stand, it knows how to like move one leg, or some basic primitives it already knows, right? But then you're asking it to mix these basic primitives and do more complex maneuvers, like say, even be on a skateboard. And so that's also enables transferability because with the control paradigms, these basic primitives, we know how to make them robust, right? Especially in like a four-legged system, which is still, which is in equilibrium, right, at by default. So those are the areas where we can get a start, right? We take in the existing techniques and ask, how do we improve that with machine learning while maintaining those guarantees? And then ultimately, over time, we can make more of the components learnable and be more efficient.
All right, so let me seize on one of the phrases you use with black box AI, right? That's one of the major criticisms, obviously, of AI. And there are these two different schools of thought where just with more data, more deep learning, it will lead up to more stable and predictable AI versus, this path of current deep learning algorithms is not leading to anything, it's not sustainable. Therefore, the future of AI is in the mix of symbolic, maybe deterministic, and AI approaches. Where do you stand in that maybe academic debate, but it also translates to real world products where currently it really is a mix of neural nets and deterministic solutions?
So I think, to me, that the debate, as you said, right, is academic in the sense, to me, the exact methodology is less important as opposed to what it can accomplish, right? So indeed, this is a black box, and I mean, the whole aspect of explainability is sometimes, it's ill-defined, right? Explainable to whom? To say a policy person or to a child or to a dog. I mean, so that always becomes challenging, because what is the language in which to explain? But instead of focusing on that, what is, I think, useful is to think about how humans on average would interact with such a system. Right? What would make it trustworthy? And to me, the most important aspect is uncertainty calibration. When on average, I mean, you're on the street, you're driving, right? And another average human being, you kind of know how they would react, right? And how they would, say, are they going to come to a stop here? Are they going to slow down? So at least on average, you have the general sense. But with AI systems, when they fail very differently from humans do. And not only that, they tend to be very overconfident when they fail. And that, to me, is very problematic, right? Because I think we are psychologically tuned to thinking, oh, it's a machine, it should be perfect, because we're used to standard software that would do large multiplications, do complex math, and be very accurate. And so with that mindset, now we are interacting with these systems and expecting them to be very perfect. So if it says it's 99% confident, right? And so we tend to trust those systems. So especially in healthcare, or thinking of using face recognition, say in law enforcement scenarios, right? This becomes very sensitive. And that, to me, is the first step, right? For that trustworthiness and for real world deployments. Can we have systems that are humble, that can at least be like, okay, I'm not so sure, right? And then one of the works we have recently done is to show how this is possible by judging if these test data that we are seeing now, how similar it is to the training that the model has already encountered, the training data. And so if it is very different, at least, there is like a red flag, right? And there's a lower confidence. And to me, that's a start, right? But because we humans, we do that very intuitively. I mean, if we see something very new, we haven't experienced that before, there's like an alarm bell that goes off in our mind. And that's said to be the first step towards consciousness, right? It's being aware of the surroundings, it's being aware of our own limitations and our capabilities. And that, to me, is a great start.
Okay. So let's talk about the next frontier then. These are all the issues, but how do we get to that AI? Right now I see AI as augmenting what people do, not replacing. So one question is, do we need AI to replace what people do? Do we need AI to be better than people? And how do we get there? What are the issues? Kind of an open-ended general question, but where do you think we're headed with this?
Yeah, and that's where, to me, it's not one size fits all, right? Now we are going to different domains and asking, what can AI do here? So think of examples of scientific simulations, right? Like doing very complex fluid turbulence, like on an aircraft wing, or, like climate change, right? Like predicting climate for the next 50 years. These require now, even on supercomputers, it's extremely expensive. For instance, even with the world's best supercomputer today, with the current traditional methods, if you want to predict the climate over the next 10 years, right, with a single setting, it requires all of that run, right? So like a week or something more. So this is what we're talking about. Like, it's very, very expensive to do these computations. Or another example is, computing the quantum states of the current molecules. If you want to ultimately predict properties of drugs, that, if you go to the quantum level, that is the most precise calculation you can think of, right? Because it is going to be accurately predicting the binding energies. So in that sense, it's a very well-defined problem. I mean, if you want a precise drug to bind to a certain protein, if we could search the whole space, we would have done it. But that's 10 to the 60 possible molecules, right? So it's, really limited by computation more than anything else. It's a completely well-defined problem. But how can we now go from traditional tools that are infeasible to AI learning some underlying representation and making the relevant approximations to better target towards drug molecules. And so these are things that currently, don't involve a lot of humans, right? Sure, there is human involved in tweaking or kind of like using the current judgment of what would be a good molecule, but it's still inherently compute heavy. And those to me are prime ground for augmenting or even ultimately being replaced by AI. The recent methods we've developed is, in many scenarios from 1,000 times to 1,000,000 times faster than existing tools, and that's all the way from, modeling climate change to fluid turbulence, carbon dioxide, storage, all these problems that are deep science that's very important. So that's one category, right? So, when humans are not involved to begin with, it's to me very well defined and straightforward, but a challenging problem for AI.
So you used a phrase about humble AI, how AI should be humble. So it triggered a question in one of our participants, Donna Hoffman. She says her research focuses on consumer perception of AI. Your idea that AI should be humble is really interesting. How are you thinking that AI algorithms, et cetera, could communicate something like that to a user? So what does it mean for AI to be humble?
Yeah, and and that's where, right, because even confidence levels and probabilities, it's sometimes hard to communicate, right? So one question is, I think I'm not the expert here, but I would imagine we would need further careful studies in terms of seeing how humans, right, are reacting to different confidence levels and what's the best way to communicate. Potentially having like a cartoon character, right, that would, ideally not that is gendered, because there's also issues of, especially making that feminine, as we see in many cases. But yeah, I'm not the expert, but I think we can come up with creative ways to drive home the point, like, oh no, but just be very careful here, take this with a grain of salt.
All right. I'm going to turn to a question from a pre-submitted question. Back to kind of MLOps stuff. And, this is a question from Andrew Schumann with Arch Systems. How do you see AI actually driving things in the enterprise in the next 5 years? What should we expect beyond marketing AI? Basically, beyond the hype, what will be the substance of AI in the next 5 years in the enterprise where it really matters? So talking about hardening, AI for enterprise applications.
So indeed, and to me, that really comes from building end-to-end workflows and pipelines, right? And making that specific to different domains rather than all purpose, because we've seen a lot of good development in saying, okay, let's train this on multi-nodes. We do have some good tools to do that, or to do distributed reinforcement learning. We have, right, enterprise support for that now. So, but how do we go from those general purpose tools to, let's say, a platform, right? What would a platform for healthcare look like? And what we're building at NVIDIA is many different threads there, right? Because drug discovery, I mentioned earlier, it goes all the way from like the search space to docking, right, to looking at molecular dynamic simulations, all these very, very complex algorithms. Not all of it is AI today. Not all of it is efficient today, right? So how do we make these pipelines interact well and be seamless, and eventually look to ways to replacing traditional methods there with AI, right? If it's easy enough and convenient enough to gather training data and check whether AI is relevant here to be replaced, I think that's, to me, an exciting area, like, having now a platform view and thinking of more vertical solutions tailored to the end user and the domain expert rather than just an AI expert.
I see. So I think you've answered the question from another pre-submitted question from Anshuman Pandey. He basically said, what is your take on MLOps and startups in this space, the future? What should startups working on MLOps focus on? So any startup opportunities that come to mind, as advice to our audience?
Yeah, and I think that's, to me, it goes back to working backwards, right? I think that's a principle that's, to me, very important. Like, what is the problem you're solving rather than AI as the solution? Maybe AI is not even the solution, right? And now, as you said, like the AI hype is mostly, right? That cycle is maturing, which is great. So, but people are looking for real solutions. So it may not be the most glamorous problem, right? But there are so many areas where, there's even the basic digitization has been slow. So, but those are ripe for disruption because we can quickly build end-to-end systems and solve challenging problems. For instance, I think, to me, also thinking about those problems that would benefit humanity, right? So we talk so much about climate change, but how do we build platforms that would, for instance, help us tackle this, right? And what kind of AI methods at scale would help us do this? Or drug discovery, I keep going back to that. But those are just some examples that require heavy compute, that require AI, but are much more than that, right? It also requires deep domain expertise. And we'll see more of that where it won't be just purely AI.
Yeah, and I like the suggestion of, also focusing on unglamorous problems that are often the most impactful as a platform, as a core technology, that lead to vertical solutions. People don't often enough focus on problems like that. They're actually really impactful. All right. So more questions. Alan Miller. It seems like the current generation of computing is a result of a big advance in networking. Since then, processors have advanced radically, but networking is largely the same. Do you think the next step in AI is really waiting for a radical advance in networks rather than processors? I think it goes back to data movement. With such massive amounts of data, how can we move all that data? How do we get it to the processor?
Indeed. And, at NVIDIA, we think about this a lot, right? And with MLOps, we do have the state-of-the-art networking connections as well. And then the next now question is, how much of in-network computing can we do? Can we have smart switches, and can we, make that also be ultimately predictive, right? Because if we can understand what kind of data that would be moved and how that would be compressed best, then we would get good end-to-end performance. But yeah, I think that's also the aspect, because it's no longer just about a single GPU, right? The DGX is really about putting these GPUs also with the fastest interconnects possible, because otherwise you're just limited by that. And we are no longer, having small enough models or small enough data sets. We are in the now regime of multi-node training, so we would need these very fast networking as well.
Yeah, and like you said, NVIDIA is addressing that through the acquisition of MLOps, also NVLink for GPU to GPU and GPU to CPU data transfer. But also there are a lot of startups working in optical networking. And one that really is fascinating to me is free space optical data transfer, because that leads to almost infinite bandwidth, but is of course very difficult and challenging to implement. But Indeed. Those are some of the directions I'm aware of.
Indeed.
All right. Here's another question from a former NVIDIAN as well, Hadi Nahari. He and I actually overlap there. Objectively, how much will GPU be part of the next generation of AI, both in inference and training? So basically, GPU is the present of AI compute. Is it also the future of AI compute?
Well, I believe so. And yes, certainly I have some amount of bias, right? But it's an informed one, but it's also one, the reason I continue to be here and develop all the exciting technologies. And to me, the primary reason is that the CUDA platform we have with millions of developers, right, and the ability to quickly adapt to new neural network architectures, right? Now transformers are breaking through the roof, right? And, they are relatively so new. Tomorrow it'll be something else, right? So for this diversity of different workloads and these aspects, the software is more important, if not as important, right? So it is such an important aspect of it. We do want very good hardware efficiency, and we continue to develop that. We want more beefy GPUs, more memory. All this is growing, but the important thing is the ability to easily program new architectures, because this is still a greenfield, right? As I said, this is the golden era of algorithmic development. So it's not like this is a solved problem. We've figured out ResNet 51 is the best architecture ever, and everything would be running on that, right? So, and I think with that dynamic changes, we need one that is flexible at the same time efficient. And so that's what we see with the MLPerf results, right? Year after year, we are able to essentially cover all the categories, whereas most of the others are barely able to do one or two. So I think it's the versatility that to me is the winner.
Yeah. Well, as a former VP software at NVIDIA, I agree that software is more important. You're absolutely right. All right. A question from Mark van der Berge. Hope I said that right. What do you see as the future of natural language learning and dialogue management? Well, what is the future of NLP?
So indeed, I think, we won't be, we will continue to grow the models, but not at the enormous rate we saw over the last few years, and probably not by much more, right? Instead, the focus will be on, really making these models more robust, right? As I said, more consistent. Can we ensure that they align with some knowledge bases or rules we have, about hate speech, for instance, right? Like, or biases, and how do we carefully check this? Because, you can give a few prompts and you can be like, oh my God, it makes the babysitter a woman and a stock trader a man, right? But just fixing that doesn't solve the enormous biases that are in there. And that's such a difficult question. And, how do we separate the factual ones from ones that are not true, right? Like, indeed, women on average are paid less. So that statement has a bias, but it's factual. So that's such a hard judgment, right? How do you decide this? And first of all, having a model that's one size fits all. It has fiction about unicorn to math, right? So we've just kind of taken everything into this big soup. And that's really not, to me, the right thing to do. And we see this now with the medical language models, including the ones from NVIDIA. What we are doing is, based on medical journals, can we just train models there? And can we look at specific tasks based on this? It's still a long way from giving diagnostic advice directly from the model, right? But what would get us to a point where it's trustworthy, where it would understand the context, and where it would be able to at least give some quick pointers, if not the actual, answers. I think those to me are very meaningful.
So we had a pre-submitted question, kind of a different twist on trust, because it introduces the word ethical. How does the ethical AI transform trust that does not exist with black box AI? So ethics is a little different from trusting and facts and things like that. So what are your thoughts there? Yeah,
indeed. To me, we need to involve policymakers, social scientists, right? People from all these other areas who do that for a living, right? Who are experts in ethics. And that's only possible if we can have some level of interpretability and explainability, right? And to me, I go back to the starting step of having humble AI that can at least truthfully give the confidence levels. And on top of it, we can have gold standard tests. So if you see the gender shade studies that came out a few years ago, at that point, the National Institute of Standards did not even have good representation of all races in its own gold standard dataset, right? So if the Standards Institute is not doing it, then there is no hope for the rest of the companies to follow that. So coming up with what are the right guidelines? What is a good representative dataset? And it need not be one dataset, but an array of tests, we know the set of tests for a car to be road ready or a plane to fly. What would that take for AI in different scenarios? And who comes up with those tests, right? And how do we say this has passed the test? So I think that also requires domain experts and ethicists to be part of that conversation. And then finally, right, all this requires good user interfaces. UI tends to be not, again, a glamorous thing people worry about. It's like, okay, let's just get an UI engineer and put together something. But that's no longer tenable, right? How do I understand this 500 billion model, parameter model? And so, can I look at different kind of rules and see how, what are even the rules I should populate, right? What are even the tests? And then it should also be dynamic. I should be able to quickly change those. I think, we should move beyond the tensor board. I mean, I love tensor board, right? Or even weights and biases, which is a great step up from tensor board, but to a much higher level of abstraction of what these models are doing.
All right. Moving on to some more questions. Alan Miller actually has a follow-up question. Do you think there is a danger that we are heading towards another AI winter? If so, is there a way to learn from the past and avoid this? Basically, is the field going to stagnate? Do you see any signs of that?
I think the field is in a great place today. I'm glad that the hype is not just building up to infinity, right? Because that's ripe for an explosion. But instead, there is reality check. There are rightfully more awareness of bias and these deep problems with the models, but also, looking at practical solutions for that, right? And involving, having this very inclusive notion of people from other domains and expertise. I think that aspect is what will keep us growing.
All right. Question from Jim Burham, kind of bringing us to a more grounded reality. How are we going to manage all this data? Every minute, 100 hours of video is uploaded to YouTube, equaling, I don't know, some number of petabytes per day. That is obviously huge and enormous. And, we just keep, how do we manage that?
Yeah, I mean, and it depends on the context, right? Like, mentioned social media. And that's indeed like right now the companies have, kind of said, okay, let's just, let people do what they want. And that's not tenable. We've seen deep societal outcomes from it, right? And so misinformation that is propagating and people dying as a result of that. So there has to be a much better set of rules on what kind of content do we allow online. And, in most cases, the most problematic content, right? Like if you look at anti-vaccination content, most of the content is by, say, 10 influencers or so, right? And recently, I think there was a move to ban many of them. So, yes, there is the problem of lots of data and how to moderate it, but the viral ones and the very big problematic ones are still, easy for human moderation, right? It doesn't require AI. And so I think that to me is already a good place to tackle, and then we can worry about the long tail after that. But if you're looking at other domains like sciences, right? Like the satellites today discard most of the data. They don't even transmit it back to Earth. Or I was at CERN recently, right? And so the particle accelerators, so much of it is discarded, right? Like there's so little of it recorded. So the question is, what are we missing from this? Are there lots of nuggets that are gone? And how do we, better handle this? And I think that to me is where AI could be very powerful, because it could pick out new insights.
No, I dealt with this problem firsthand in self-driving cars, because an R&D car collects 1 to 2 terabytes of data per hour per car. So do you keep saving everything from every single sensor, or what do you discard? It's a tough problem, because if you discard something, you don't know what it was. It could be some really key thing that happened on the streets of San Francisco or elsewhere. And, there's still no easy.
And that's where you could use AI to decide that, right?
Yeah,
Ultimately, you want to ask, and that's also the AI that would know the generative space, right? I think I like this quote by Richard Feynman, that what you cannot create, you do not understand. So for AI to ultimately reason and understand, it has to be able to generate. And so, we've seen good progress with generative models, but that's still the infancy. So ultimately, if it's understanding, what is this generative model of data, and should I keep this new data, or is it very similar to the ones I've already seen? I think those kind of algorithms can really help us deal with this.
Right. Joe Rafa asks a question that also very specific to NVIDIA, but it's interesting because just the nature of how dominant NVIDIA is. What is the biggest threat to CUDA? And is there one? Or is CUDA basically the de facto standard? What is the biggest what? Sorry, I missed. Threat to CUDA. CUDA, NVIDIA's CUDA language.
Yeah.
What is the biggest threat to CUDA?
Threat. Okay, I didn't hear.
Right. I'm sorry.
It was distorting each time.
Right.
I think to me, right, CUDA is really about democratization of GPU programming, right? So when my colleague here at Caltech, Peter Schroeder, he tells me he taught the first course with GPUs, and when CUDA came along, the attendance just greatly increased, and there was so much excitement. And I think to me, that's what makes NVIDIA special. Right. And in fact, Jensen Huang, our CEO, likes to tell the story. The day CUDA was launched, the stock price went down to $1 some cents. So, we don't always just go by what Wall Street thinks should be the right thing to do. Right. And building a platform like this was enormously intensive and hard. But once it's there, I think it really makes it easy for people to build new algorithms. And, AI was not even in the roadmap, right? It came along and tomorrow it could be something else. But what's important is building the right foundation and the right primitives to speed up matrix methods, and now even tensors, right? So if we can build that foundation, we can build a lot of great structures on top of it. Actually, I like that story from Jensen. I joined NVIDIA in 2007 when CUDA 1.0 was launched, and the stock crashed soon thereafter. I thought it was me, but I guess it was CUDA after all. So, of course, you can never see if there's a causal link, but I think No, I do really respect that story, and it's not probably told often enough. CUDA 1.0 was in 2007. AlexNet, ImageNet was in 2012. We worked on CUDA for those 5-6 years relentlessly with 5 customers, in the entire world, and all of a sudden CUDA enabled this huge growth opportunity for NVIDIA as a company, because again, thanks to the brilliance of Jensen and others within NVIDIA who saw the need for something like this to enable GPUs to grow beyond just video games and graphics and things like that. Anyway. Indeed, it's hugely inspiring to me. And, like even yesterday, right, Raj, what we were asking is what can it do for science, right? What can it do with the Clara platform? What can it do with SIMnet? I think all these are now, to me, ways that we can really build tools that greatly benefit humanity. All right, let's turn to some of the pre-submitted questions. So Ernest Prabhakar, we use the word determine in the title of this Robochat, how, data algorithms and compute will determine the future of AI. Ernest says, determine is a strong word. Are there any non-technical factors that might override that future or impact it in some major way? Well, certainly in terms of, we do want stable democracies, and we want, right, to make sure there is peace and there are no wars. So, and hopefully we'll continue to have that. At least that's an immediate one that comes to mind. Yeah, so those are the non-technical factors, right? Okay. Cameron Techland asks, with the coming and underway AI revolution, aside from work, how will it affect how we play and relax? What's quality of life improvements thanks to AI? Yeah, and this is where I think we need to be careful about, right? Because we're going, 24/7 connected and,
Yeah.
even essentially monitored and surveilled, right, by all the apps we use. And so, at some point, if we rely too much on it and we are hyper connected, how it affects our mental and emotional health is something, we've seen, especially vulnerable population like teenage girls. You saw the recent report on what Instagram can do, and that was the case earlier with, say, magazines and Photoshop, but now that has been amplified a lot more, right? So we do need to be mindful of the dangers, and the question is, do we regulate that like tobacco, or are there ways that the companies will see that it's for their own benefit to be transparent on both the good and the ill effects? So I would say that on that aspect, I'd rather just dance and play without any tech. Just go on a hike, go rock climbing. So I just really wanted to be low tech.
All right. We have only a few minutes left, so maybe one or two more questions. Another question from Hadi Nahari, ex-NVIDIA. Thoughts on self, semi, supervised learning? So basically the different types of learning, and how do we deal with untagged versus labeled data? Where is the field going? Because labeling is a huge labor-intensive process. That's also probably not sustainable or scalable.
Indeed. And I think there are several directions here, right? So one is, what if we had just weak supervision? So one of the recent works, we call it Disco Box, that'll appear at ICCV, is to ask if you only had bounding box supervision. So it's very quick to just put a box around, right? It's not a lot of human labor, as opposed to segmenting everything, like, what we call instant segmentation, right? So meaning every human being in the scene, you want to segment and make that very precise. So those aspects, if we can learn through this only weak supervision and with a combination of self-supervised learning, because you can add internal consistency in terms of what should an instant segmentation look like. And that's what we're able to show. We're able to show very precise segmentation using just box supervision. And also ultimately, like correspondences. With correspondences, you're getting an idea of which parts, right, correspond across different images. So you're getting more of a 3D view of what's in the image. And again, these are very heavy for labeling. So the question is, can we use lightweight labeling to then do these harder tasks? I think that's one way. The other is synthetic to real, right? Because on synthetic, we get complete supervision for free. But then there is a domain shift. So what we've done recently is come up with methods that can do this transfer by trying to retrain on real data, but ensuring that we only retrain on the confident labels. And that's where uncertainty estimation becomes important. So I think it's these kind of algorithmic development, right? Because ultimately, if what humans do, what we do as infants is to do self-supervised learning, right? We are just looking around, and it's theorized that it's the occlusions, like we are kind of looking at, we're moving the head and we are kind of figuring out what's in the foreground versus background, and that is the foundation of our perception. And indeed, a lot of the current self-supervised learning improvements show promise. In fact, for many classification tasks, we are even beating the supervised baselines. Right. So, which says that, if you look at the invariance in data, right, you crop parts of the data, it should still be invariant. You add certain kind of noise, you rotate it. So all this are, invariances we can teach the model. And that to me is very promising.
All right. So we're pretty much out of time. I can't thank you enough for your wisdom and insights. You're truly inspirational, with your success and your activities. We get a lot of high school and college students, in our audience. Any parting advice for them? How should they think about their future in this new upcoming AI world?
Yeah, I think, the aspect is to focus on your passion and see what you can do to benefit humanity, right? So think of always the long term, and at the same time, use all the tools that are being developed to build that solution, right? So I think the future is really bright.
No, I like that. Do something meaningful. Exactly. We like to at Playground, we like to say, work on things that will have a multi-generational impact. So we don't work on dating apps and social media. We do deep tech, truly impactful stuff, that will help everybody. Well, thank you so much, Anima. It was a pleasure talking to you, and I hope to see you soon again.
Thank you so much, Sasha. And thank you for sharing your NVIDIA experiences that made this conversation even richer.
Thank you so much. All right. And thanks everybody for joining. We'll see you at our next Robochat. Bye, everybody.
Bye.